Hello and a warm welcome back to Mr. M for Chem's YouTube channel. Trust you find this an interesting video. It's all about the chemistry of the alkenes, as the title suggests. First of all, a huge, massive thank you to Knockhardy Publishing for allowing me to use their PowerPoints at this time during the pandemic and helping to educate students for many years and hopefully many years to come as well. So we'll start with the basics. The alkenes are CnH2n. You can see on the right hand side that I have been playing with WebMo again. I've been building the simplest alkene, which is ethene. We have 1, 2, 3, 4, 5 sigma bonds, and we have 1 pi bond. Okay. We can calculate, as I was just doing, the electrostatic potential of this molecule, and we can spin simple ethene around, and we can see that the red area, which is the high density or high electron density, is around the pi electron cloud, which we can clearly see here is above and below the plane of the molecule. Spin this through 180, spin it through 360, and we can see just where the electron density is in a simple molecule of ethene. So let's start with the basics. Can you remember what is a covalent bond? What's the difference? When do we have homolytic fission? When do we have heterolytic fission? So homolytic, you are right, we have that when we have free radical homolytic fission. So that's the alkanes, with normally chlorine in the presence of UV light forming free radicals. Heterolytic, that's when we have an SN1 or an SN2 reaction, and we'll be looking at those in a different video. Balancing simple equations, we're going to assume you all know how to do that. Write simple structures for hydrocarbons, and some branched structures as well, but still quite simple. And then look at the gradation in physical properties as you would expect with any homologous series as we work through this video. So they are members of a homologous series. A homologous series, remember, if it asks you to define this, a homologous series differs by 1 CH2 unit. Hydrocarbons contain only carbon and hydrogen. You must say only to get the mark. CnH2n for non-cyclic alkenes, and cyclic alkanes. Unsaturated just means, it's an old term, it just means there's room for more hydrogen. You could have different atoms, you can have bromine for instance. It tends to be for hydrogen, and there is a C double bond C somewhere in their structure. As you can see from my WebMo little build here, we have a perfectly planar molecule. Look, it's perfectly flat. We can see down the axis of that molecule, and as we transcribe these angles here, 360 divided by 3, so it's 120 degrees. These solid dashes come out of the plane of the board or the plane of your screen and point towards you, and then the white wedges here, which would normally be the hashed wedges, will point into the screen here. So if we can just line this one up with what we see on the left hand side, it's something approaching this, isn't it? Let's get it a bit straighter. There we go. Beautiful. Pi bond in the middle and sigma bonds on the outside. Planar, 120 degrees. Clearly, this is the IB. They're of course going to ask you, what are they going to ask you? They're going to ask you about the hybridisation, aren't they? You should all know that carbon is 1s2, 2s2, 2p2. We can draw the electrons in boxes. If we provide a bit of energy, what we normally say is the hydrogen surrounds the carbon atoms, distorts the energy fields. They then become equal in energy. A 2s electron, this one that was here, can jump from here into the p. So now instead of 2p we have 3p. Instead of 2s2 we have 2s1. It is favorable because the arrangement of electrons for unpaired with lesser repulsion is more stable. So if you have two electrons in boxes, they are repelling each other. They're pushing each other apart because they have actually a formal negative charge. They're going to repel like negative charges always have. So it's energetically more favorable for this one to jump into here and form these three unpaired electrons and one unpaired electron in the 2s orbital. The four orbitals combine, or what we say is they hybridize to give four new orbitals. They're brand new, they are hybrids like a Tesla or a Toyota Prius. It was this jumped over into here. This had a spherical shape. S comes from spherical, P comes from principal, D is diffuse. It's all from spectroscopy when they first discovered these. What was the 2s1 is now degenerate, is equivalent energy with the three P's, the px, py, pz. So we now have, instead of two unpaired electrons, we have four unpaired electrons. This is sp3 geometry. And these are now able to undergo bonding, typically with hydrogen. That would have been for the alkanes, sp3 for the alkanes. sp2, however, is what happens with the alkenes. We still have the mixing of atomic orbitals to make hybrid molecular orbitals. So we have the S sphere from the spherical mixing with the P principal diffuse, that would be px, py, pz on the relevant axes, to form an orbital with some S character and some P character. But what's different now? What's different is that the PZ, I don't want to say the PZ, I've seen it different orbitals, but let's call it the 2p for the sake of argument. One of the 2p is unhybridized, this one here. And the unhybridized orbital is, of course, the pi orbital. The hybridized sp2, that would be carbon-carbon, carbon-hydrogen, carbon-hydrogen in a molecule of ethene. So alkanes, sp3 tetrahedral, 109.5 degrees. However, in alkenes, it's sp2 trigonal planar, 120 degrees. Covalent bonds are the overlap of orbitals, and the ones that are intermediate between the nuclei here along the principal axis, we term them a sigma bond. So these are the hybridized bonds here, and it's this orbital overlap of sp2 hybridized molecular orbitals. We could see on the WebMo the clear regions of high pi electron density. This is one pi bond above and below the plane of the molecule, above and below the plane of the molecule, and that's only one pi bond. That's often confused or often poorly described, elucidated, described by students, that this above and below, that's here and here, you can see the red, almost like the sun going down on the horizon, is just one pi bond. Okay. For maximum overlap and the strongest bond, the two p orbitals are in line. Very good. So review, 2sp2, sigma bond, pi bond, this is the pi bond, beautiful drawing, better than I could ever do. Pi bond above and below, one of them given a trigonal planar, 120 degrees. We can move on now? We can move on. Okay. Naming. Same as with any of the organic chemistry molecules we've been covering, we're first of all looking for the longest chain. It's not always immediately obvious what is the longest chain, right? Because sometimes they draw it going around corners and things, and you have to count the longest chain. Well, let's keep it simple to begin with. So select the longest chain, okay, and we can have a go at building this molecule. At the bottom, what's this molecule here? 1, 2, 3, 4, 5, 6. So it's got 1, 2, 3, 4, 5, 6 carbon atoms. They are all have a sigma bond in between each of them. On carbon atom 2, on 2, there is a double bond. So we have a pi bond here, And on 1, 2, 3, 4, 5, see what I did there, 1, 2, 3, 4, 5, we have a methyl group. I can clean up, idealize my molecule, and now the beauty of WebMo is that I can spin this molecule around, have a look at the geometry, and just see how it's actually arranged itself in space. We can see it's 5-methyl-hex-2-ene, but this has got the 2 here, and this has got the 2 here on the other side. But we're still thinking 1, 2, 3, 4, 5, 6 is a hex. 1, 2, 3, 4, 5, 6 is a hex. The homologous series is the alkenes. The double bond, the lowest number for the double bond, is on carbon atom 2. 2. So this is a hex 2-ene. You could have hex 1-ene or hex 3-ene, but this is a hex 2-ene. Since the functional group dictates the numbering, 1, 2, 3, 4, 5 methyl. So this is not 2 methyl, 4 hex 4-ene. It is 5 methyl, 1, 2, 3, 4, 5, hex 1, 2, 3, 4, 5, 6, 1, 2, ene. Okay, so we need to, if there is a choice where the double bond could be, which here clearly there is on 1, 2, or 3, we need to put the number in. And we start our numbering from the lowest number of where the double bond is. Okay. In a separate video, we had a look at structural isomerism. I've just been mentioning here we could have 1, 2, or 3 in this case because it was a hex. But for pent, we can have pent 1-ene, 1, 2, 3, 4, 5. Pent 2-ene, 1, 2, 3, 4, 5, but it's on 2, not on 3. And don't forget, we're always checking our molecules to make sure carbon is always bonded to 4. Always 4, never less, never more, 4. So that's 1, 2, 3, 4, 1, 2, 3, 4. You can count 4 all the way. If you can count 4 in a neutral, uncharged molecule or moiety, then you're good to go. And it's often a mistake that students and some teachers sometimes make, where they'll put an extra hydrogen in here for some bizarre reason and make it a pentavalent carbon. That's something you must not do. Clearly, all of these have the same molecular formula, but this is pent 1-ene, pent 2-ene, and of course we can branch it. We can take off this methyl group, we can pop it onto, take off this one actually and put it onto here, and make 3 methyl. So don't forget 1, 2, 3, 4. Longest chain is but 1, 1-ene, and 1, 2, because 1 was the lowest number for the functional group. 1, 2, 3 methyl, but 1-ene. Jolly good. Geometric isomerism. All textbooks start with these pair of likely suspects. Or they start with this one, or they do but 2-ene. This looks like, I suspect, this is 1, 2 dichloro. That's nice. What a nice green. 1, 2 dichloroethene. You already said that, didn't you? Okay. Clean it up. Let's clean up for geometry. Okay, about the same. And I do like to just have a look at where the electron density is, because that tells me often where the organic chemistry is actually going to happen. So I can spin these around. They're still flat molecules. But remember how pronounced the pi electron density was above and below here. It's still pronounced, it's still there. But look at the difference now. This massive chlorine atom here, with its 3 lone pairs of electrons, high electronegativity. This one is lined up in a kind of negative-ended stick, if you like. It's almost flat there. Look, it's got lots of electron density here and here. This one has a different symmetry, a different shape of the electron density. This is low, this is high. Okay, so this is going to have a very strong dipole between it. Okay, we need to think about that because it's going to give us different physical properties. Okay, how do you know if you're going to have geometric isomerism? Well, just looking at the molecule, two different groups at either end attached, yes, you can. Two the same groups at the same end, no, because you could swap this around, but all you're doing is swapping whether you're looking from the bottom up or from the top down. Make sense? Okay. Or if you've got two similar groups attached to either end, two of the same groups attached to either end, that means like on this side, two the same here, one there, you cannot, because you're just flipping it round in space, you're just moving it through 180 degrees. And then two different atoms or groups attached, all different here, well, yes, you can, okay, because the connectivity will be different. It will depend on the electronegativity values of each of these, how that will manifest itself in physical properties, okay. So, to get to geometrical isomerism, we need to have two different groups attached at either end, and they can be identical or non-identical, as long as they're not repeated or duplicated on either end. Geometric is an example of stereoisomerism, and we get the isomerism because there is restricted rotation, I can say it, restricted rotation around the double bond. If you think about a single bond, okay, and you just think about good old ethane, we spin around ethane, around this sigma bond here, don't forget these are all hybridized in ethane, it's sp3, this has got free rotation, this can spin around this bond, no problem. But as soon as I put a double bond between the two carbon atoms, in fact, let's start again. 1, 2, double bond. By putting the double bond in, I prevent free rotation around here. If I was to twist those two carbon atoms, the sigma bond is able to rotate. Because the pi bond is on either side, as we've been showing, that pi electron density, we would have to break it to actually spin it around. So when we have different groups on either side, we need to communicate which isomer we have. We use the words cis and trans, and we use the CIP system, which we'll come to shortly, for Z and E. They are not always equivalent on the naming system. If this is chlorine, as we were building, this would be cis 1,2 dichloroethene. This would be trans 1,2 dichloroethene. Cis means same side, so these chlorine atoms are on the same side, and trans means opposite side. They are clearly opposite to each other across the double bond. So we've seen that single covalent bonds, sigma bonds, can easily rotate and spin around, but double bonds cannot. So I cannot take this molecule, remember the name of this? Cis 1,2 dichloroethene. I cannot spin it and make it trans 1,2 dichloroethene because the pi bond stops me from doing that. Cis and trans should only be used when there are two hydrogens and two non-hydrogen groups. Okay, the non-hydrogen groups could just be a halogen, it could be a carboxylic acid, it could be an amine, it could be a group as well as just one single atom. Cis, same side, trans, opposite side. So what would we think about these molecules here? Longest chain, 1, 2, 3, so it's a propene. We've got chlorine on here. So if we put the double bond in the middle, students often struggle with, given a molecular formula on a piece of paper. So it'd be C3H35Cl, C3H5Cl. They often struggle drawing that with the double bond in the middle of the page, particularly when the question is going to be going towards, as often does, a geometric isomer. Hydrogen has low priority. Why does hydrogen have low priority? Because it's little bitty hydrogen. It's atomic mass of 1. Methyl has got 15. If that is chlorine, it's going to be 35.5. So my biggest, heaviest atoms are on the same side of the molecule here. But here, they're on the opposite side of the molecule. This will be cis and this will be trans. It's kind of obvious. You can look, if you put the double bond in the right place where you are drawing it, and the biggest groups are on the same side, it's cis. If they're on opposite sides, it's trans. Is it that simple? No. The second system we use is E and Z, and I'm glad that the German words are here. I always forget them. E is Entgen, forgive me any German speakers, and zusammen for Z. Okay, E is enemy, opposite sides. E is enemy, and Z is same side. Okay. So here we have the cis isomer. Okay, and the cis isomer on the same side will be the Z isomer. That works because it's a nice, simple example. The CIP, or the Cahn-Ingold-Prelog system, is based on the idea of what I was just saying. Hydrogen is the smallest thing. It's always going to have the lowest priority. And anything that has a higher atomic or molecular mass will have higher priority. So in this case, ethyl has greater priority than methyl, has greater priority than hydrogen. And clearly iodine at the bottom, if we ignore astatine, is bigger than bromine, as bigger than chlorine, fluorine, hydrogen. So lowest priority, highest priority. Highest priority is highest molecular or atomic mass. Lowest is lowest atomic or molecular mass. Let's have a look. Here, look how we've drawn it. Again, the double bond is in the middle of the piece of paper. I can see what's the longest chain. 1, 2, 3, 4, 5. 1, 2, 3, 4. So it's 5. So it's a pent. 1, 2, 1, 2, 3. So it's a pent 2-ene, isn't it? You're looking, you're thinking. Can you say whether that is cis or trans? Is it trans because the methyls are on opposite sides? Is it cis because, oh, but that's ethyl and that's methyl. The cis-trans system only works for very simple examples. So that's why we need the CIP system. So let's look at the molecular masses. 15 for methyl, 29 for ethyl. Good to remember for mass spectrometry. 15 and 1. So the bigger atoms, the bigger molecular masses are on the same side. So have a look, put it down the middle. What's the higher priority groups? 15 beats 1 on the left. 15 beats 1 on the left. And 29 beats 15 on the right. So I'm taking a mirror or a razor or a rope, whatever you want to call it, down the middle of that double bond. That's why it's important to draw your molecule with the double bond in the middle of the piece of paper. Which is the higher priority group? Clearly 15 beats 1, 29 beats 15, so it's same side. So this is the Z isomer. Okay, we could then be asked to draw the E isomer. So if you have a look, you put the piece of rope in the middle of here, a mirror. This is 1, this is 15, 15 wins. This is 15, this is 29, 29 wins. So 15 wins here, 29 wins there. They are enemies. The highest priority is on opposite sides of the double bond. The key to solving these and getting them correct is putting the double bond in the middle of the piece of paper. Okay. Some examples here. What's this one? 1, 2, 3, 4, 5 pent 2-ene, 3 methyl pent 2-ene. Is that cis or trans? 15, 1, 15, 29, 15, 1, 15, 29. EZ. This one was 15, 1, 1, I assume chlorine 35, so same side. Here E, opposite side. EZ isomerism. 3 structural isomers of C4H8 that are straight chain alkenes, no rings. Okay. But 1-ene, but Midgley eats pink biscuits, but lowest number 1-ene. This is in all the textbooks. Cis sim side 115, 15 wins, 115, 15 wins. This side 115, 15 wins, 115, that one 15 wins. So cis trans ZE. But remember, when the groups get more extended, the cis trans ZE system is not always in agreement. Okay. Physical properties you would expect, with more branching, a lower boiling point. Longer chains, higher London dispersion forces. I'm kind of assuming you know all that. A mechanism. So we have, with our beautiful alkenes, a wonderful double bond, which is able to be attacked. So this molecule, if Mr. Midgley remembers to put his double bond in, that's better. This molecule is this lovely region of electron density, and we can have something called an electrophile, something that loves electron density. So let's have something nice and polar that loves electron density. And when I draw this little beastie, oh, look at that, hydrogen bromide. Hydrogen bromide clearly has a permanent dipole. It has the relatively positive hydrogen, 3 lone pairs of electrons around the bromine, HBr massively negative. So this is a dipole dart. Okay, do use that word. It's a dart. It's dying to attack. This region of electron density, the pi electron density, will want to attack. Will want to attack that hydrogen atom on the HBr. Okay. Look, the arrow comes from the double bond to the hydrogen. From the double bond to the hydrogen. I often see students do it from the hydrogen to the double bond. If you put the head of the arrow to this, wrong. From the double bond to the hydrogen. This is also a concerted mechanism. That means it happens in concert. It happens together. As the double bond attacks the delta positive, slightly positive hydrogen, the pair of electrons in the bond between the H and Br, they jump onto the bromine and form the Br minus ion. This is heterolytic fission. Heterolytic. Homolytic, 1 electron to each of the atoms from the molecule, like chlorine in the free radical chain mechanism. Heterolytic, where both electrons come from that bond and sit on a bromine atom. There is an intermediate step. There is always an intermediate step, isn't there? Okay. What's the intermediate step? Well, as this bond breaks, the pi bond breaks, the hydrogen that's being attacked by the double bond sticks to either this one or this one. It doesn't matter. You will never know. It depends where you are sat. You could be here or there. It doesn't matter. Where are you? One of the carbons, doesn't matter which one, will have then a formal positive charge. Carbon hates having a formal positive charge. It's a really, really unhappy bunny. But thankfully for this carbocation, this big atom here, pretend it's bromine, this bromine atom, now has a formal negative charge because it got that pair of electrons from that heterolytic fission of that bond, and that can quench or satisfy that positive charge on the carbon, forming bromoethane. Electrophilic addition, C2H4, HBr, bromoethane. We just went through that. Steps, the HBr nears the alkene. HBr nears, yes. The pair of electrons attaches to the slightly positive end of the HBr. Yes, it does here. It leaves a positive charge on the carbocation. Then the bromine, fast step, bumps straight onto there. Bromoethane is your product. The bromide is the nucleophile and attacks the carbocation. Nucleophile loves positive nucleus, positive sites. Okay. If we add bromine, Br2, this is the standard test for an alkene. How would you know you had an alkene? Shake it with bromine water, it decolorizes. Why does it decolorize? Same mechanism, but slightly different explanation. Previously, we had HBr with a permanent dipole in the molecule. Now we have BrBr with no dipole. But here it's saying there's delta plus and delta minus. How did that happen? It happened because as the pi electron density here, that we saw over on our WebMo molecule, as that approaches the bromine, it's going to push electron density away in the bromine molecule. So like charges repel, it's going to make one end of the Br2 slightly negative, which means relative to that slight electronegativity, the other end is slightly positive. As soon as that happens, same mechanism, bosh, it's just the induced dipole rather than a permanent dipole, as in the HBr. Then it's the same, the double bond attacks, heterolytic fission. Instead of hydrogen, one of the bromine atoms attaches here, and then we have a formal positive charge, the second bromine atom, 1,2-dibromoethane. That's the standard test you've been doing since you were 14, 15 years old, testing for unsaturation using bromine water. Okay. Another difference between this and the free radical mechanism for addition of chlorine to alkanes is there's no UV light required here. Okay, we do it at room temperature. No catalyst is needed. It's also heterolytic rather than homolytic fission. They do sometimes ask you to compare and contrast homolytic and heterolytic fission. Give examples, 6 marks. This is what you need to be describing. So again, it's nonpolar. It approaches, induces a dipole. The Br2, BrBr becomes polarized, and we get 1,2-dibromoethane. To do the physical test, just shake it. Just shake it. If it decolorizes, double bond, alkene. Easy as that. Ethene is a symmetrical alkene. What happens if we add to an unsymmetrical alkene? Because when we do that, we then introduce choice of outcome. Okay. So you are all intelligent chemists, and here are 2 identical molecules of propene. And we're going to use our permanent dipole for our HBr. There we go. Here's our Br, and here's our H. Just going to bond it there. And we can just clean those up. That's good. So we've got our HBr, we've got our propene. Is this the same propene as that propene? Yes, it is. You could be stood here or there. If you were stood here, the double bond would be facing you. If we stood here, it would be facing you, be on different sides. So they're exactly the same molecule. Okay, same molecule on here. Let's get them so I can see them. There we go. So we have 2 choices. We have a choice. That double bond is still going to attack that delta positive permanent dipole hydrogen in hydrogen bromide. We're still going to break this bond. The double bond is going to break. We're still going to get heterolytic fission, that pair of electrons jumping onto that bromine atom. We get the carbocation in the same as the previous example. But on this route, we get 2 bromopropane. 2 bromopropane. So it's added onto this atom here and here. Don't forget, same molecules. But the double bond could break and positive charge could go here, or double bond could break and positive charge could go here, right? Statistically, it looks like it's a 50-50 probability of either outcome. So let's do that. Break the double bond. The positive charge for the carbocation is not now on the central atom, it's on the terminal atom, and we'll make 1 bromopropane instead of 2 bromopropane. But guess what? When we do the reaction, 99% is this isomer, is 2 bromopropane. Why? Well, that carbocation, that formal positive charge, is much more stable when surrounded by bulky, bigger groups. So in our example, we had the positive charge for the predominant product, the major product. The positive charge is on the central carbon atom. There are adjacent methyl groups. They're called positive inductive effects. They're pushing electron density in, stabilizing that positive charge. Whereas here, we have an ethyl group, yes, which is bigger than methyl, but here we have a little teeny little hydrogen, which has got negligible, zero positive inductive effects. So this is much more unstable on a terminal atom. Positive charge is much more unstable on a positive atom than it is on a central atom with groups surrounding it, stabilizing that positive charge. So here, secondary carbocation is much more stable than the primary carbocation, as I just explained. We do get a little bit of this one, a little bit, but 99% is going to be this is going to be the major product. Okay, and that's actually called, the proper term is Markownikovs rule. There's the word for today for you, Markownikovs rule. Okay, we don't need to know that. We do need to know this. Hydrogen with alkenes will make an alkane used in margarine manufacture, GCSE. Polymerization, this one is the one that normally messes students up. This one, ethene, they go, yep, I can draw a repeat unit of polyethene, break the double bond. This has got round brackets, square brackets, doesn't matter. N could be 1,000,000, this is 1,000,000 repeat units. And then when asked to draw the repeat unit of polypropene, they forget that this term and this methyl group is north or south of the chain, and that's where it needs to be before you put the brackets in. Okay, so this again is GCSE stuff. So addition polymerization is what alkenes undergo using a Ziegler-Natta catalyst. We all know the problems with polymers, recycling, toxic, burn waste, all those things. So in summary, halogenoalkanes can eliminate using hot alcoholic solution. They eliminate from halogenoalkanes. We'll be doing this in a separate video. The decision between substitution and elimination. Or you can dehydrate alcohols to make an alkene. You should be able to do all of those things. I hope you enjoyed today's video. Thank you very much indeed for watching. Don't forget, electrophilically add to the subscribe button. Thank you very much indeed. Have a great day. Stay safe. Thank you.